Hello everyone and welcome to the PCD for Codeforces Round 1040 Division 2. Um, this is TLE Eliminators and I'm Vibhaas and we'll be discussing the questions now. Before we start, can you mention in chat if the audio is fine? And also, how was the contest, guys? How was the contest? Okay, some people didn't get A, B, and some people solved C, and a lot of people did solve D, some got D as well. Okay, right. I also found it a bit on the tougher side. I started like 10 minutes late because I forgot to register. So I did late registration and I didn't quite get D. Although in today's session, we'll discuss A, B, C, D and a little bit of E1 as well. So we'll discuss A, B, C, D, E1, all of them. Okay. C was hard because you didn't know graphs. To be honest, there's no graph algorithm used in the solution of C. You just had to use basic logic related to graphs. Okay. Anyways, so yeah, I can see you people have a lot of questions. So when we get to that particular question, you can ask them, right? And especially general doubts, we'll handle at the end of the session. All right. Okay. So before we get started, as you know, if this is your first time on the channel or if you have not, decided yet, do check out teliminators.com/courses where our self-paced courses are live right now. Um, as you can see, there's a sale which is there for like the remaining 20 minutes, right? So if you register like within the next 20 minutes, you can get the sale. Um, so do check out our self-paced courses. They're split across 4 different levels where we teach competitive programming, all the way from the beginner, completely newbie starting out level, all the way to the expert level. So if you finish level 4, ideally you'll be able to hit expert, right, with enough practice. It contains more than 40 hours of recorded lectures, more than 100 plus curated practice problems, instant video solutions for all the problems, as well as doubt support and progress tracking, right? So go do check it out. If you reload, you will get the sale thing. It's on the top, yeah. Anyways, so without further ado, let's get into the questions. The first question was pretty simple, so I won't spend that much time on it. Problem A, submission is all you need. For a multiset T consisting of non-negative integers, we define the sum as the sum of all elements in T and max of T as the smallest non-negative integer not in T. So this is the standard definition of sum and max. So sum is simply the sum of the elements and max is the smallest integer not in the set, right? So in 0, 1, 1, 3, max will be 2. You're given a multiset S of size n consisting of non-negative integers. At first, your score is 0. You can perform the following operations. Select the subset and add sum of that subset to your score, then remove the subset. Or select a subset and add max of the subset to your score and remove that subset. And we have to find the maximum possible score that can be obtained. Okay, we have to find the maximum possible score that can be obtained. How do we approach this problem? Okay, so let's quickly get into it. Problem A. So basically, we're given an array, and let's say our array is like 0, 0, 1, 2, 1, 1, 0, 1, 2, 3, 4. Okay. Now in this array, we can take any set of elements. For example, multi-set of elements. For example, if we take these, we can remove these elements and we can increase our answer by the MEX or the sum of these elements. Okay. So either we increase our answer by the sum, which is 2, or we increase our answer by the MEX, which is also 2 in this case. Okay. So as you can see, we can increase our answer by the sum of the MEX, 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 right? Which is the minimum element not over here. So as you can see, 0 is here, 1 is here, and 2 is not over here. So we can increase our answer by that much. All right. So how do we solve this problem? There is not much to it. There's just a simple observation that, let's say you want, let us consider, when can the MEX be greater than the sum? Okay, when can the MEX be greater than the sum? So when can MEX be greater than the sum, right? So whichever is the best, we will choose that at each term. So when can the MEX of some subset be greater than the sum of the subset? So this is only possible, observe, if our subset S dash or some like multiset S dash is equal to 0. Okay, it has only one element and it is 0. And why is that? Because now the sum over here will be 0. Meanwhile, the MEX of this will be 1, since 1 is the smallest element not present in this multiset. Okay. So if there is like zeros over here, then only the MEX will be greater than the sum. Okay. If you take any other multiset, if we take any other multiset, for example, let's say we have 0, 1. Okay. In this case, the sum will be 1 and the MEX will also be 1. Okay. What if we had 0, 1, 2? Okay. In this case, the sum will be 3 and the MEX will also be 3. Okay. What about if we had 0, 1, 2, 3? Okay. In this case, the sum will be 3 plus 2 plus 1, which is 6. Okay. In this case, the sum is 6 and the MEX equals to 3, right? So as you can see, when we get more and more elements, here the sum and MEX are staying the same. And as we add on more elements over here, the sum will become larger than the MEX. So it's usually always better to use the sum operation instead of the MEX operation. Only when the multiset is equal to 0 element, then the MEX is better than the sum. Okay. So this is the key logic behind the problem. Um, I hope you're following this, right? So the key logic behind the problem is this. On which problem are we? Currently, we are discussing the problem A. Okay. So the key idea over here, uh, key idea, key idea. It is always better to use the sum operation instead of MEX, except for except for the case where chosen subset has only zeros. Okay, chosen subset is a subset which is like a zero subset. Okay, so there's only one zero. In that case, the MEX will be more than the sum. Okay, and that is the only case where the MEX can be more than the sum. So here is our final idea. So final solution using this observation is that um, for all the zeros in the array, for all the zeros in the array, we will take MEX, right? In the array, we will take the MEX, take MEX operation, right? And that will basically increase our answer by 1. So that will take the answer, increase our answer by 1. And for all the elements which are non-zero, for other elements, we are going to simply use the sum operation, since that will be greater than or equal to MEX. Take the sum operation, and that will be simply just increasing answer by A of I, right? That will be simply same as increasing answer by A of I. So this is the final solution to the problem. Okay. So we can solve this pretty simply in big O of n, and I'll show you the pseudocode for it. Okay. So I'll show you the code itself for it. So we take in n, we initialize our value, answer or sum or whatever, to 0. For each element x, we input x. If x was 0, we have to add 1. Otherwise, we have to add x to the sum, right? So that's what this logic does. If it's 0, it will add 1, adds 1. Otherwise, adds x. Okay. And I hope you can understand that this is what it does. Otherwise, adds x. I wrote this in one line, like, just shortened the code a bit. This is what this code does. And then finally, we can print the sum. Okay. So, yeah. And that will pass all the cases, right? Using our logic. Okay. So let's move on to problem B, right? Shivam, Coder, and the people who say discuss problem B, discuss problem C. Look, it is not easy for everyone, right? For some people, problem B is also very easy. For some people, problem D is also very easy. So we'll discuss all of them one by one, spending the appropriate time. Okay. Anyways, let's move on to problem D now. If anyone has any doubt in problem A, please put it in the chat. Okay. Problem is 0, 1, 2, 3. Okay, yeah, MEX is 4. Right. But that still doesn't change my observation that the sum will be larger than the MX. But you're right that the MX is 4 here. I just made a mistake while writing that. Yeah. Okay. Nice observation. But yeah, that does not change the fact that the sum will be better than the MX all the time. Yeah. Okay. Okay, let's discuss problem B now. Pathless. Right. There is an array A1, A2 till AN consisting of values 0, 1, and 2. Okay, so this array consists only of the values 0, 1, and 2 and an integer s. It is guaranteed that A1, A2 till AN contains at least 1, 0, 1, 1, and 1, 2. Okay. Alice wants to start from index 1 and perform steps of length 1 to the right or left and reach index n by the end. When Alice moves, she calculates the sum of values she is visiting and she wants the sum to be exactly s. Okay. So basically, Alice is going to start at position 1 and reach position n, and she wants the sum of the visited elements be exactly s. So here they've given a formal definition. You can read that if you want for what they mean by like visiting each position. However, Bob wants to rearrange the elements of the array to prevent Alice from reaching her target. Determine whether this is possible, right? So we need to find out if there's some way to prevent Alice from reaching her target. Okay. And if there's some rearrangement, we have to print that. Fine. If there's some rearrangement which prevents Alice from reaching her target, we print that. Otherwise, we can print -1. All right. And there are some test cases, right? Okay. All right. Okay, yeah. Here, who put this in the chat? Yamala Glams says that, okay, for 0, 1, the MEX is 2. Okay, right. You are quite right about that. The MEX is 2. Yeah, okay. So here there's a interesting thing which happens. So if you take the sum approach, right, the value is 1. Meanwhile, if you take the MEX, it's 2. But what you do over here to solve our question is, okay, yeah, so this is a bit of a subtle test case. But basically what we're doing to solve our question is, if you take MEX of 0 plus sum of 1, okay, so take the MEX of the 0 element and the sum of the 1 element, you again get 1 plus 1 or 2. So that's why this thing does not really affect our answer. But yeah, this is a bit exceptional. So, okay, nice catch. Again for problem A. Yeah. Yamala glance, you are correct. It is 2. But however, this does not affect our answer mainly because if we, instead of this, we can just simplify it to having a MEX of 0 plus sum of 1, right? So in our solution, what we did was we basically, this was the final solution we wrote. For the zeros, we take the MEX operation, and for the other elements, we take the sum operation. And again, we can see that in this special case as well, that does not change our answer. So if we take MEX of 0 plus sum of 1, it remains 2. Similarly, if we take these together and take MEX, it's also 2. So that's why it works. Right. Thank you for catching on. Yeah, we already were in B. So um, just someone put that on the chat, so I addressed it. Anyways, so for problem B, let us discuss what they mean by a valid path, right? So at first, let's discuss what they mean by a valid path. So let's say we have, so the elements of the array can be only 0, 1, 2. and there will also be at least 1 0 1 2. Okay, so pay attention. So let's say our target sum. So Alice's target sum, Alice target sum, that's equal to 20. Okay, the target sum which Alice has is equal to 20, and let's say our array is equal to 0 0 2 2 1 0 2 1 0, something like this. Okay, and then basically what Alice needs to do, she needs to start walking over here. Alice needs to start walking over here. Then she will go somewhere like this. Maybe she can come back as well. That's what she can take one step in any direction. That's what's defined as a path. And then finally, when she has like taken all her steps, then she should reach the end of the array. Okay, she should reach the last element, and then the sum of all the visited values, that will be the sum which she has acquired, and she wants to find the target, like she wants to make it equal to the target value. Okay, so for example, if we have a path like this, here, here, then we go one back, we go front again, then here, here. Okay, then what is the sum we get? We get 0 plus 0 plus 2 plus 2. So we went from here. Now we came back again, right? Because we came back, we are adding these two elements again, right? These two elements got added twice because we went back one step and went forward again. Then plus 1 plus 0 plus 2 plus 1 plus 0. Okay, so Alice's path has the following weight, following sum. And this sum you can see, is it equal to 20? It's equal to 10, 11, 12. It's equal to 12, which is not 20, right? It's not 20. But there is some way for Alice to make it equal to 20. For example, we know that if we repeat this, it will add another 4 to our answer, right? So if we repeated this twice more, it would have become equal to 20. Okay. So now how do we basically, reach our target sum? So the first observation we should have, the first observation, which is very obvious on reading the question. So observation 1, if our target sum S, okay, so our target sum which Alice wants is S. If S is less than the sum of all elements, okay, is less than sum of all elements AI, right? Then the answer, then any array works. Any array works since um since just to go from element 0, just to go from element 0 or element 1, element 0 to element n minus 1, let's say, exceeds S. Okay, exceeds S. So this is the first observation. And what do I mean? I basically mean, let's say our target sum was 5, and let's say we have our elements as 2, 2, 2. Okay, then if Alice starts here, she goes here and goes here, it's already equal to 6. Okay, Alice's sum has become 6, so it has become more than our target. And no matter what, any way we arrange the array, it will always make Alice like lose her challenge. So that's why for this case, if there's a trivial answer, we can print any array for this case and it'll be valid. Okay, so I hope the trivial case everyone has understood, right? Just output the direct array, just output the array, right? Anyways, now what next? Okay, so we have to understand what it means for Alice to traverse a path. And here we can make a simple observation again. Observation 2. And it's basically, let's say Alice has given an array like this, okay? And her target is, let's say, 10. Now, if she simply takes a normal path going through all the elements, her sum will be 1 plus 2 plus 2 plus 2, which is 7. Okay, so her normal sum, like if she takes a normal path, the sum is 7. Okay, now the thing is, here we're at a 1, right? So what if we went back and we went forwards again? Okay, if we went back and we went forwards again. Okay, so when we are at this 1, we'll take a step back and then we'll take a step forwards. Okay, then what happened is basically we are adding these two elements again. Okay, so if we take a step forward, take a step backward, then forward, then forward again. It's basically adding one to our answer. Okay, it's basically adding one to our answer when there's like 0 and 1. Okay, so at this 0 and 1 position, it's adding one to our answer. So if we do this at some position I, is basically going to add the value a of I plus a of I minus 1 to our answer, right? If at a of I we go back, it will add this value, and then we come forward again, it's going to add this value. So basically it will add a of I plus a of I minus 1 to our answer. Okay. So if Alice repeats this enough times, she can keep adding 1 to our answer until the sum becomes equal to the target, right? If Alice gets a 0 and a 1 next to each other, then Alice can just keep repeating this until the sum equals her target. Okay, so I hope you understand this. If at any point Alice has a 0 and a 1 or a 1 and a 0 in the array, then Alice will be just repeating this until she reaches her target sum. Okay, her target sum was 10. She just repeats this 3 times and she will reach her target 10. Okay, so basically, if if the first condition is there, if S is greater than or equal to A of I, right? So this must be noted. If S is greater than or equal to A of I, and there is a 0 followed by a 1 in the array, then Alice will always be able to reach her target. Okay, then Alice will always be equal to will always be able to reach her target. Fine, because then she'll just repeat that 0 1 many times until it equals her sum. Okay, so basically we need to avoid this. Our array should not put should not put zeros and ones together. Okay, so whatever our array will be, we will not put zeros and ones together. Fine, our array will not put zeros and ones together. So basically what our array will look like is all the zeros will put in the start, then we'll put the twos in between to stop or block them, then we'll put the ones in the end. Okay, so I hope you're getting this. We're going to put all the twos in the start, and then we'll put all the zeros in the start, twos in between, and ones in the end. That way 0 and 1 will be far apart, so Alice will not be able to use this method to cross. Okay, okay, I hope you got that right. uh okay, but there's still some ways Alice can cross. And how is that? Like Alice can reach her target sum, because what if she repeats these two? Okay, so let's say Alice was going along that path like this, and then she repeats these two, right? Then again AI plus AI minus 1 will be added. Here it's equal to 2. Okay, so if we have an array which looks like this, and obviously there must be at least 1 0, at least 1 2, at least 1 1. So this will be the smallest possible array. In this also it's possible. She starts at 0, goes to 2, comes back to 0, right? So this will add, basically this operation is like for Alice, her sum will increase by 2, right? Her sum will increase by 2. Fine. Now what if she is here and again she does this? So she goes to the next step and comes back again and goes front again. In this case, her sum increases by 3. Fine. So if she repeats a 0 2, the sum will increase by 2. And if she repeats a 2 1, her sum will increase by 3. Okay. So I'm hoping what you're understanding what I'm saying. Basically, I'm trying to say, okay, screen freeze, it's fine now, right? Okay, fine. So basically, what I'm trying to say is, if you take a step forward, like basically what Alice is doing is taking one step forward, one step backward, one step forward, right? So what this is essentially doing is adding these two elements again. And if we have all zeros in the front, all twos in the middle, all ones at the end, then basically the two operations available are add a 2, add a 3. Okay, so basically the operations available now, the operations available to Alice now, available to Alice now is add a 2 or add a 3. Okay, is add 2 or add 3 to make her sum equal to target. Okay, to make her sum equal to the target. Fine. So now we have to see in which cases can she not equal her target. Fine. So let me take some examples. let's say my starting sum is 5. So the sum of all the elements is 5. And my target is my current sum is 5. And my target is, let's say, 10. Okay, can I add 3s and 2s to convert 5 into 10? And we can see that it is possible. 5 plus 2 plus 3 is equal to 10. Okay, what if my sum was 7 and my target was 11? Okay, in that case we can simply add 5 plus 2 plus 2, sorry, 7 plus 2 plus 2, and then it becomes equal to 11, right? So we can see that most of the cases Alice is able to solve it, right? In fact, which case is she not able to solve? So basically our problem reduces to um, given x equal to target minus initial sum, right? Target minus initial sum. So in terms of the problem, this will be s equal to x equal to s minus sum of a of I, right? X equal to sum s minus sum of a of I. Can we split x into sum of zeros and twos? Okay, sum of zeros, sorry, sum of twos and threes. What am I saying? So sum of twos and threes. Okay, so this is basically what we need to find out. If we can prevent Alice from, if we have to prevent Alice from reaching her target, then she should not be able to split this x value into sum of twos and threes. Okay, so basically what this problem reduces to is showing that if you take sum of twos and threes, you'll be able to form any number except one. Okay, so this is math observation. Math observation. If you can take sum of any number of twos and any number of threes, right? If you can take sum of any number of twos, sum of any number of twos, any number of twos, and any number of threes, right? Any number of threes, we can form any number except one. Okay, we can form any number except one. Okay, any number except one. Fine. And let me show you how. So one we cannot form. Okay, two will be simply two, three will be simply three, four equals two plus two, right? And five equals two plus three, six equals two plus two, right? Seven equals three plus two, 8 equals 2 plus 2 plus 2 plus 2 plus 2, right? 9 equals 3 plus 2 plus 2 plus 2, right? So basically, as you can see, the even numbers are just adding a plus 2 to the previous even number. Similarly, the odd numbers are just adding a plus 2 to the previous odd number. So basically, using this operation where she's able to add 2s and 3s, she's able to make any target as long as that target is not just one above her starting point. Okay, as long as that target is not one above her starting point, she'll be able to reach any target. Fine. So as I hope you can understand. So basically, what I'm trying to say is, um, so the first case, obviously everyone understood that if S is less than sum of A of I, then it's not possible for Alice to do it, right? So any array will be fine. Now what we did was we showed that zeros and ones should not be put together, because if zeros and ones are put together, Alice will always be able to reach her target. So what we're doing is putting all the zeros in the front, twos in the middle, and ones in the end. Okay, and if we put all zeros in the front, twos in the middle, and ones in the end, what happens is Alice can basically add twos and threes and try to reach her answer. So the only place this fails is if her target is exactly one more than the sum. Okay, so basically, Bob can prevent Alice from doing this, right? Bob can prevent Alice from doing this if, yeah, Bob can prevent Alice if we have the following two conditions: either um, S is less than sum of A of I, or the S minus sum of A of I is equal to 1. Okay, so if X is equal to 1, the X which I defined here, right? X is target minus initial sum. So S minus A of I, if this is equal to 1, then Alice cannot reach it. All right, so these are the two conditions. And then what array should be output? In the first case, any array works. Any array works for this case. Any array works. And for this second case, we need all the zeros and ones to be separated. So we can output an array where all the zeros are in the front, all the twos are in the middle, and all the ones are at the end. Okay. So these are the two cases. Otherwise, the answer is -1. Okay. Otherwise, -1. Fine. This is the full solution to problem B, or the way I did it. Okay. If there are any doubts, please. Okay. Can you repeat? Yeah, there will always be 1, 1, 1, 2, and 1, 0, right? I will repeat this just in a bit and explain what I did here. What might be the rating? I guess 1100. That's my max guess for this problem. It is a bit complicated, but yeah, 1100 or 1000, I guess, seeing the number of solves as well. Okay, so here you can have a look at the code. Input n and s. We have our initial sum. This variable counts the number of zeros, ones, and twos. Okay, so it counts the number of zeros, ones, and twos. So I input x and I add that to my sum. Okay, so each value gets added to the initial sum. If my initial sum is greater than s, so this is the first case. This is the first case. If my initial sum is greater than s, it's just written in reverse. That's all. So this is the first case. If my initial sum is greater than s, we know Bob can do it. Or if my target sum minus my initial sum, so my target sum minus my initial sum is equal to 1, right? If my target sum minus my initial sum is equal to 1, then also we can do it. And what do we have to do? We have to print all zeros first. So while the zeros are while the zero counter decreases, we print zeros, and then we print all the twos, and then we print all the ones. Okay, so we can print this like this. Otherwise, it's not possible, and we can print -1. Okay, and why did we do this again? Basically, we said that. Uh, basically, we said that if we had a 0 and a 1 next to each other in the array, okay, if we had a 0 and a 1 next to each other, then Alice can repeat these two elements. Okay, what does repeat these two elements mean? She's doing her walk, she goes back and comes front again, right? So in that, what will happen is basically the sum, the sum of the walk which she has traveled, right? The sum of the walk which she has traveled will increase by 1. And if it increases by 1, she'll always be able to reach her target. That's why we are not keeping it with zeros, ones, twos, or something like that. That's why we have to ensure that 0 and 1 do not touch. Okay, so that 0 and 1 do not touch in the array. As long as you make any array such which follows this, your answer will be correct. Okay, do not touch. Fine. Now what we need to do is, so one such array is, for example, all zeros followed by all the twos followed by all the ones. Okay, so how many ever ones, zeros, and twos were there? So we make such an array. Now Alice gets to repeat this, which will increase her score by 2, and Alice can repeat this, which will increase her score by 3, right? So if the zeros and ones are not touching, obviously the zeros and twos will touch somewhere, and the 2 and 1 will touch somewhere. Okay, so that should be obvious. And this increases the score by 2, this increases the score by 3. So basically, we need to check if can she reach her target by adding 2 or adding 3s. Okay, and I showed here that that is only not possible if her target is exactly one more than her sum. Otherwise, it will always be possible by some form of repetition. And that's why we get this final solution. Okay, I hope that's understandable. It's just a math problem. There is some observations because there's path and stuff. So yeah, it will be 1000 or 1100 max 1100, I guess. Although seeing the number of solves, it might as well be 1000 or maybe even 900. Yeah. Okay. All right. So this question is clear. Let's move on to problem C. Okay. Sorry if my voice isn't that clear today. I have a bit of a cold, I guess. Slight cold. Anyways, problem C. Okay, so this problem is pretty nice in my opinion, but I can see why if you're not used to graphs, you might find it a bit confusing. For a set of pairs, we define f of s and g of s as follows. Okay, so we're given a set of pairs. Each element is like ai bi form. Okay, first f of s we are going to define, and How is that defined? Treating each A of I and B of I as the segment or number line, as the segment on the number line, and f of s is the length of their union. Okay, f of s is the length of their union. So formally, f of s is I hope you understand what union of segments means. But basically, it's the length of all the integers x which are covered by this by these segments. Okay. Now, what is g of s? G of s is treating each a of I, b of I as an undirected edge in the graph. G of s is the number of nodes which lie on at least one simple cycle with three edges. G of s is the number of nodes which lie on at least one simple cycle, right? So basically, we're going to make a each a of I and b of I as like nodes of the graph. So then in that case, it will become the number of simple cycles in the graph. Okay, so it will be the number of simple. It will be the number of nodes in a simple cycle. Fine. Now we are given a set. So we are given a set, and they give us an example of how it's done. So we'll see some examples as well. Now you're given n distinct pairs. Your task is to select a subset such that f of s dash minus g of s dash is maximized. Okay, we have to maximize f of s dash minus g of s dash, and we need to output the indices of the selected pairs. Okay, my first and only observation was no, that and this is kind of incorrect. Fabid, your observation is not correct. Anyways, yeah, I was also not able to solve D, but we will get to its solution as well. Okay, so let's discuss the solution for this. So first, let's take an example. Okay, take an example. We'll understand the question. Take example, and let's take their example itself. S equals to 1, 2, 2, 4, 1, 4. I think the quarters was pretty nice, even if I was not able to solve much. Um, the questions were pretty different from what you see usually. Okay. So first we'll do the first operation, which is the union of length of segments. Okay. So operation one, length of union of segments. Okay. Length of union of segments. Okay. So for this, I'm just going to draw a number line. I'm going to draw a number line. And so as you can see, there's the points, the intervals marked here are 1, 2. Then there's an interval like 2, 4. Then there's an interval like 4, 5. And there's 6, 7 as well. Right. So I'm just marking some of these important points. And if you take union of this, so there's an interval 1, 2, there's 2, 4, there's 1, 4, there's 4, 5, and there's 6, 7. Okay. So if you take the total length of the union, so what will be the union over here? The union will be this and this, right? So the length will be over here, the length is 4, right? 5 minus 1 is 4. Uh, and here the length is 1. 7 minus 6 is 1. So here it's 4, here it's 1. And you can see that f of s is equal to 5. Okay. So that's what length of union means. We're simply treating it like intervals on number line and we're doing union. So if you have ever heard of Klee's algorithm, it's an algorithm used to find union, although it's not used here, obviously. But yeah, this is what the algorithm, this is what the union of segments means. Okay. So now what does the second operation say? Second operation says we treat it like a graph and these are the edges. Okay. So the operation 2 says we treat it like a graph and these are the edges and we need to count the number of simple cycles. Okay. So then let us make all the nodes of the graph first. So let's call this node 1 and then so each number will be a different node, right? So node 1, 2, there is 4, there's 5 and there's 6 and 7. Okay. 1, 2, 4, 5, 6 and 7. So these are the nodes of the graph. Now there's an edge between 1 and 2 and there's an edge between 2 and 4. There's an edge between 1 and 4. Okay. Now there's an edge between 4 and 5. There's an edge between 6 and 7. Okay. So now what is G of s. So G of s is simply the number of nodes in a cycle. Okay, so number of nodes in a cycle, and as you can see, these three nodes are in a cycle, right? These three nodes are in a cycle. So here G of s equal to 3. Okay, so if you take f of s minus g of s, the answer will be 2. And basically, we need to somehow remove some intervals so that this is maximized. Fine. We need to remove some intervals and we need to maximize this. Okay. So let's get into the problem and try to understand. So okay. Now, one interesting thing to understand is how f of s and g of s are related. Okay. So basically, let's understand. Let's think of the intervals. Let's think of the intervals. So this will require some intuition related to like the number line or like geometry type of intuition. So let us think of the intervals and how a cycle can form and how a cycle can form in terms of the intervals. Okay, in terms of the intervals. Since we're trying to minimize the number of cycles or the cycle nodes, and we are trying to maximize the area, like the length covered by the intervals. Okay, in terms of the intervals. Okay, so let me just draw a number line, and let's say we had an interval like this. Fine. And then we had an interval like this, and then we had an interval, let's say like this. Okay, so what does this mean? If you take the graph view, this point, let's call it point 1, this point, let's call it point 2, and this point, point 3, we can say that there's an edge like this between all three of them. Okay, because these two share the common node, these two share a common node, these two share a common node, so a cycle is formed. Okay, a cycle is formed. So that's what it means to go from the interval perspective to the graph perspective. Okay, and here you should get an intuition. So here you should get this intuition idea. If here you can see two nodes, like two starting positions of the edges are at the same starting position, right? Like this interval and this interval, they have the same starting position, right? So here's an idea. What if the intervals we chose, what if the intervals we chose had different starting positions? Okay, had different starting positions each time. Okay, different starting positions. Fine. What if all other intervals we chose had different starting positions? And in that case, what happens basically? Let's say we chose this one, and we chose the orange one, okay? And then we chose the pink one. So we only chose the orange and pink one and not the blue interval. Fine. And basically that will mean that this edge vanishes, and there will be no cycles. Okay, there will be no cycles formed. If in our chosen set, in our if our chosen set of pairs S dash, there are no two with the same starting point. No two, no two intervals have the same starting point, right? Have the same starting point. Starting point. Then for G of S, no cycle will be formed. Okay, no cycle, no cycle will be formed. Will be formed, and we can say that G of S dash will be 0. Okay, G of S dash will be 0, and this is good for us. Why? Why is this good for us? Because we want to maximize f of s dash minus g of s dash, right? We want to maximize this value. And if g of s dash is always 0, then our problem will simply become f of s dash we need to maximize. Right? We need to simply maximize f of s dash. If we if we can somehow maximize it while keeping in mind that we can only choose for each left point, we can only choose one interval. Okay, so each starting position we can only choose one interval. If we can somehow do that and still get a large f of s dash, then it's very good for us because there'll be no cycles at all. Fine. So I hope you're following this. Okay. So now the next observation is simply um, for each left position, for each unique, like for each AFI, each unique AFI, right? AFI in the AFI BFI wala jo set tha, a set of AFI BFI values. Choose the one with largest BFI. Okay, choose the one with largest BFI. Okay, so for each unique AFI in the set which we are given, right? So here we are given a bunch of numbers. As you can see, 1 and 2 are there, and 1 and 4 is also there. So we'll only choose the one which is larger. Okay, we'll choose 1 and 4, and we'll not choose 1 and 2. And we can show that the length of union will not change if we do this. Okay, the length of union of all segments does not change when we do this. Doesn't change when we do this. Okay, why is that? Because see, if you're starting at some position, right? If you're starting at some position, let's say on the number line, you're starting at some position x, and you have two intervals. One is going to x plus l, and one is going to x plus, let's say, r. Okay, so one interval is like this, and one interval like this. So obviously, if you drop the smaller interval, this interval is redundant, right? The smaller interval is redundant. We can just drop it, and it will not change our answer at all. Right, because the length of union will anyways include all the points from x till x plus l, right? So the larger one, which is L over here, larger length one, that one will be the one which we will keep, and we'll remove the one which has the smaller right point. Okay. And what does that do? That basically makes sure that first it makes sure that g of s is 0. Second, it makes sure that f of s dash does not change. Okay, does not change in this method. So basically, what is our solution? Our solution is um, for the pairs. So this is going to be solution for the pairs a of I, b of I. Keep only unique values of a of I. Keep only unique values of a of I. If multiple a of I are there, like the same a of I appears multiple times, a of I's are there. Pick the one with the largest b of I. Pick the one with largest b of I value. Okay, so you can make many implementations of this. You can use sorting, you can use maps, whatever, as long as you achieve these two things. Okay, and why are we doing this? Because if we notice how the graph works, right? So the graph, it only happens when two nodes share some point, right? So what we're ensuring is that no two nodes share a starting point. That way we'll never be able to form a cycle, right? So that will make sure that g of s dash is 0. Second, it's very simple how to do this for f of s dash also without changing the answer. Simply remove the smaller and redundant intervals, right? So this interval is no use because when we take union, the bigger interval will anyways cover all the points. So there's no point keeping the smaller interval. So we'll remove all the smaller intervals starting at every point. So this will be maximum, this will be minimum, and the whole expression will also be maximized. Okay. So I hope you understand how this worked, right? Yeah, and this is the max value we can achieve because the length of union in the whole thing can never be larger than this, right? Since g of s dash is 0 and f of s dash is also maximum, this is the maximum we can achieve. Let's have a quick look at the code for C. The code for C. So you can implement this in many ways. My way is maybe slightly complicated, but yeah, there are many ways to implement. So what I did was I sorted. So I took it as vector of pair, where it is the following type of pair. Okay, so the pair is a of I, comma b of I, comma I. Okay, comma I. And also one more thing, I'm storing it as negative b of I instead of positive b of I. Okay, so this is what my vector is going to store. For each pair is going to store a of I, comma negative b of I, comma I, and that's how I've implemented it. And this is what this code does. Now, if I sort this, the a of I will be sorted smallest to largest, and the b of I will be sorted largest to smallest, right? So the largest one will be taken first. Now I define minimum as my basically the AFI value which I'm currently taking, and I ensure that for each AFI value, I only take exactly one, right? So minimum means the minimum AFI value I will take. If if my current AFI is greater than the minimum, I take that one and I push that back to the answer, and I'm updating my minimum to the current AFI. Okay, so basically I'm ensuring that any given AFI, I'm not taking two. And also because it's being sorted by negative BFI, the largest one will come first, right? The largest one will come first. So that's why this is automatically giving me the correct interval each time. Okay. So the time complexity for this will be big O of n log n for sorting. Even if you use maps, still maps will be big O of n log n itself, right? For sorting the pairs. Okay, so if you're not clear on the code, you can just go through this once. You can pause the video and have a look at it. If you observe, it's doing exactly what I said. It's saying that it only keeps unique values of AFI. And if there are multiple with the same AFI, we will choose the largest BI value. Okay. Okay, so you're saying your solution, my solution is not. Okay, yeah, you're correct. Wait, okay. Famid, I'm not sure how to pronounce your name exactly, but basically what I'm saying is, um, what I thought you said was, so this is for Famid. What I thought you said was optimal f of s dash minus g of s dash will be equal to the f of the whole set minus g of the whole set, right? And this is not true. But yeah, you are correct in saying that this is true. So this is correct. This is correct. This is correct, but this is wrong. I thought you said the first thing, that's why I said it was wrong. But yeah, since you made it clear right now that this is what you wrote, you're correct. Okay. Okay. So Astonator wants me to show this implementation with an example. Okay. So I'm going to show you that it implements this solution basically. And let's say, let's just take an example from our samples. Okay. Um, we have 1, 2, 1, 3, 2, 3, 3, 5. Okay. So this is our input. So this is an example, or we can say dry run for our code, right? Okay. So let's say we have 1, 2, 2, 3, 1, 3, 3, 5. Okay. So the first thing my code does is it takes the input and it stores it in a very particular form, AFI, comma, negative BFI, comma, I. Okay. So what will that look like? That will look something like this. 1, comma, negative 2, comma, 1. So I will be 0 here. So it will be something like this. And then the second will be 2, comma, negative 3, comma, 1. Then 1, comma, negative 3, comma, 2. And then 3, comma, negative 5, comma 3. Okay. Now we're going to sort this. So now next the code will sort this, right? And what will be the sorted order of these elements? They will be, so the smallest one will be 1, comma, negative 3, comma 2. Okay. So this is the smallest one. Why? Because 1 is the smallest. And in that, B of I smallest is negative 3, right? So basically, because I wanted largest first, I'm taking negative. So now it becomes smallest first sorting, right? Okay. And the next element will be 1, 1, negative 2, 0. Right? So this will be the next element in the sorting. Then the third element in the sorting will be 2, negative 3, 1. And the final element after sorting will be 3 minus 5, 3. Okay. So this is what we get after sorting. Now our minimum element which we can choose is set to like very small. So something like this. We can see that this next element is greater than that minimum. So we will choose this. Choose interval 2. Choose interval 2. Then now our minimum is set to 1. Okay, so the minimum AFI we have used is 1. So here, as you can see, it's equal to the minimum AFI. So we will skip over here. Skip. Now here, this is greater than 1. 2 is greater than 1. So we will choose this interval. Choose interval 1. Choose 1. And we can say now that the minimum is updated to 2. Now here is 3, which is greater than 2. So we can choose this interval as well. choose interval number 3, and now the minimum is updated 3. Okay, so finally we'll print the answer, print answer, which will be 3 elements, which are 2 and 3, 2 and 1 and 3. Okay, so that's what the answer will be printed. Fine, and basically it's implementing this idea only. For each pair, we need unique values of AFI, and for each unique value of AFI, we need the one with the maximum BFI value. Okay, I hope you understand. I think specialists should be able to solve at least three. Three should be doable. Fourth one, I'm not sure. Four, maybe, maybe not. Yeah. Yeah, yeah. It was just sum of union interval length by f of s. That's all they meant. Actually, their mathematical definition was more confusing than simply length of their union. Length of union is commonly known thing. What if adding a new edge creates a cycle? Okay, see, just a pupil now, the way I did my solution was um, no two edges are going to have the same starting point. Fine. No two edges are going to have the same starting point. So what's going to happen is basically there will never be a cycle, because for a cycle you need a two starting points to occur like at the same time, right? Like for a cycle, as you can observe using this diagram, at some point we need two starting points to occur at the same node. Otherwise you won't be able to have a cycle. Okay, yeah, C was kind of easy. All right, so this is problem C. Um, let's move on. So I could only solve up to C in this contest. So I understand if D was a bit complicated. D was a bit tricky. If you got it, you got it. Otherwise, you didn't. So we'll just start D in just in a minute. Okay. But D has a pretty beautiful solution once you realize it. I could not solve it during contest. My CFID is Accord. You can see that on the TLE website if you want in the mentors list. Okay. Problem D. Stay or mirror. You are given a permutation P1 to Pn, and we have to build an array A1 to An such that either A of I is equal to P of I or A of I equals to 2n minus P of I. Okay, so either A of I equals P of I or A of I equals to 2n minus P of I. So we'll see what this operation does exactly. Find the minimum possible number of inversions of the array A1 to An. Okay, so you have to minimize the number of inversions in the array. So simply given a permutation, some elements we can change to A of I equals 2n minus P of I, and we have to minimize the number of inversions, and we have to print that minimum inversions. Okay. Yeah. So this is a bit of tricky problem, and you need a strong intuition to solve this, I think. I will explain the solution. I'm not sure how well I'll be able to explain the intuition because I didn't solve it myself. But yeah. Okay. So what does the problem say? So let's take an example. Example. And let's take the fourth example here. 5 elements, and the permutation is 2, 3, 1, 5, 4. Okay, so this is the permutation. The operation we have is value can be changed to 2 times n minus p of I. Okay. So for example, if we choose any value over here, let's say I choose this 3, I can change it to 10 minus 3, which is equal to 7. Okay. So let me just write what all elements I can change to if I wish. So this is p of I, and 2n minus p of I will simply be, it's 7 over here, 8, 9, and this will be 6, this will be 5, right? So 5 can never be changed. 5 will stay the same. But this is how the other elements can be changed if we want. Okay. So how do we minimize the number of inversions? Let us find the number of inversions in the original array. So the original array, there's an inversion between 1 and 2. There's an inversion between 1 and 3. And there's an inversion between 5 and 4. Okay. Now, one of the ways to get the minimum number of inversions is simply use this operation on 4. Okay, use this operation on 4. And what do we get? We get P of I equals, or we get A of I equals 2, 3, 1, 5, 6. Okay, so we get this, which has two inversions, and we can show that this is the best way. This is the best um, number of inversions we can get. As you can see, the answer also says 2 for this case. Okay, and like how do we go about showing that? That's another matter. But an intuitive understanding you can get by seeing, okay, for example, if we flip 1 to 9, while that will fix these two inversions, that's going to make the inversions over here worse. Okay, because there'll be a 9 before. So there's no point whether we keep it this a 9 or keep this a 1. Okay. Similarly, if we flip 2 to 8, it's going to create 4 more inversions. So there's no point doing that, right? And so on. Fine. Okay. Can I open what? Red, I did not understand what you're talking about. Okay. Anyways, so what should be our approach to this problem? Okay. So so obviously you need to like play around with the values. This contest was pretty like intuition heavy, but okay. So consider the smallest value in the array. Okay, consider the smallest value, which is 1, basically 1 in the array. Okay, what happens to 1 in our example? So we have 2, 3, 1, 5, 6. Okay, 1, 5, 6. Now, if we do not flip 1, okay, since all the values are like larger than 1, right? All the other values in the array will be larger than 1 because 1 is the smallest value. Okay, 1 is the smallest value. Now, if we do not flip 1, the elements which are on the left, these will be inversions. Okay, if we do not flip. So let's call this L and let's call this R. Okay, so elements on the left, number of inversions will be equal to L, which is the elements on the left. Okay. Similarly, if we flip this to 9, then the inversions will also get changed, right? And the number of inversions will be equal to R in that case. Okay, number of inversions will be equal to R in that case when we flip it. Okay, let me take another example. Let's say we have 4, 3, 5, 6, 1, 2, and 7. Fine. Now, if we leave 1 as it is, so here n equals 7. We have two options. Either leave 1 as it is or convert 1 into 14 minus 1, which is 13. Okay, so 13 will be the largest value and 1 is the smallest possible value, right? So we have two options. Either keep 1 as the largest value or 1 as the smallest value. Fine. So what does that do to the number of inversions? Consider everything to the left of 1. If we keep 1 as 1, then the number of inversions will be 4. Okay, number of inversions will be 4 for this case. And if we convert it to 13, then the number of inversions will be 2. Okay, so you can observe that. Just see the inversions which are responsible by 1. Okay, so basically I'm saying the inversions which 1 is responsible for, that will be 4. And I'll show you how. So as you can see, 1 is smaller than 6, 1 is smaller than 5, 1 is smaller than 3, and 1 is smaller than 4. So these are not in sorted order, right? These are not in sorted order. Meanwhile, these are in sorted order. So basically the number of inversions is 4. Okay, which are responsible for by 1. Okay, now in this case, in the case which we converted 1 to 13, the array becomes like this, right? It becomes like this, 13 to 7. Now this 13, it has no inversions with these elements. It has no inversions with these elements. The only inversions it has with the elements in front of it, right? Because um, those are smaller than 13 and they're appearing afterwards, so they're unsorted. So the number of inversions becomes 2. Okay, I hope this is clear. Basically, if the smallest element, if we don't flip, then the number of inversions will be the elements to the left. If we flip it, then the number of inversions will be elements to the right. Okay, so I hope you get this part. And no matter whether we flip or don't flip the other elements, this answer will not change. Okay, no matter whether we flip or not flip the other elements, this is not going to change. Okay, so this is a very key observation. Key observation. No matter, no matter if we flip or not flip other elements, other elements, this will not change. Okay, this answer is not going to change. This answer for inversions responsible by 1 or the smallest element by 1 is not going to change. Okay, is not going to change. Fine, I hope you understand this. That even if we flip the other elements, this answer will not change. Why is that? Because let's say we flipped 4, right? We flipped 4 to, let's say, 14 minus 4. So that will be 10, right? Even 10 is greater than 1 and 10 is smaller than 13, right? Even if this was 10 over here, 10 is greater than 1 and 10 is smaller than 13. So the number of inversions will not change anywhere. Okay, similarly, if you flipped this 2, 2 is greater than 1. If you flip it, it will become 14 minus 2, which is 12. And both 2 and 12 are greater than 1. Both 2 and 12 are less than 13. Okay, so that's why the answer will not change even if we flip the other elements. The answer which are contributed by the element 1. Okay, the number of inversions which are contributed by the element 1. Okay, okay. So now we have counted. Now we have counted. We have counted inversions by the element 1. Inversions by the element 1. Right, which was the smallest element in the array because it's a permutation. 1 will always be the smallest. Okay, so now every element larger and the inversion from 1 to that element is chosen. Let's say we greedily chose the smallest value or we did something. There can be many ways to do it. But let's just say we greedily chose the smaller value here. Okay, so we chose the, if L was lesser, then we chose to not flip. If R was lesser, we chose to flip. Okay, so basically here we can see 4 inversions. Here we can see 2 inversions, right? Here we can see 2 inversions. So we will choose this one and we will flip it to 13. Fine. So once we have chosen this, let us ignore 1 from the array. Okay, ignore 1 in the array. Ignore the 1 slash 13, whether it's 1 or 13 now. Ignore this 1 and 13 from the array since we have already counted the inversions from that element and continue with element 2. Okay, continue with element 2 and repeat this process. Okay, and repeat this process. Okay, and what will that mean? So for example, let's just continue with the same example array. So we have 4, 3, 5, 6, 1, 2, 7. 4, 3, 5, 6, 1, 2, 7. Okay. So now we converted 1 to 13 because we saw that here there are less elements, here there are more elements. So the number of inversions for 13 will be lesser. So we'll convert this to 13. And now we can ignore this. We will ignore this element. We will consider for 2. Okay. Now since 2 is now the new smallest, since we're ignoring the 13 over here, the number of inversions to the left is equal to the number of inversions will be the elements to the left of it. So the inversions, if we don't swap, don't change, number of inversions, if we don't change, is equal to 4. And if the number of inversions, if we convert this 2 to a 2 can be converted to a 12, right? So if we convert this 2 to a 12, then the number of inversions will be 1. So the number of elements to the right are 1. So the number of inversions will be 1 if we convert this to a 12. So what we can do is now we will convert this to a 12. Okay, so this is step 2 where we're fixing the number 2. So we convert it to 12. And now our array looks like this. Okay, because we're greedily converting. Now, as you can see, when we convert this to a 12, it's not going to affect no matter whether we swap, like whether we convert the other elements or not, it's not going to change the answer for the inversions formed by 2, right? So now we can see that these two are fixed and we can pretend that they're not in the array. Now we will take the element 3. Okay, now we'll take the element 3. Towards the left there is one inversion, towards the right there are 3 inversions. So that's why we won't convert this element. We will not convert to 11, not convert to 11, because on the left there is one, on the right there are 3. So if it is 3, there'll be only one inversion from this. If it is 11, there'll be 3 inversions. So we won't convert and we'll keep it as it is. Now our array looks like this. Now we can ignore these 3 elements. We can ignore 1, 2, and 3. Now what about 4? Similarly for 4, on the left there are 0 inversions. On the right there are 1, 2, and 3 inversions, right? So 4 will also stay as it is. 4 will also stay as it is. And we can now ignore it from our array, right? So we get something like this. And which elements have we already processed? We have processed the elements for 1, 2, 3, and 4. Okay. What about 5? Towards the left there are 0 inversions. Towards the right there is 2 inversions. So we leave it as it is. What about 6? Towards the left there are 0 inversions, because now we remove this, right? Towards the left there are 0 inversions. Towards the right there is one inversion, so we leave it as it is. Now 7. 7, towards the left there are 0 inversions. Towards the right there are 0 inversions. So whether we leave it as 7 or we reflect it, it doesn't matter. So let's just leave it as 7. Now we have processed all the elements. So we can say that our final answer is going to be the number of inversions in this final array: 4, 3, 6, 13, 12, 7. Okay. And this will be simply the sum of the minimum of left and right at each time. Okay. So it will be simply the sum of minimum of left and right. Here it was 2. Here it was here it was 1, right? 2, 1, 1, and here it's 0, 0, 0, 0, right? So the answer will simply be number of final inversions in this will be answer will be 2, 1, 1, which will be 4 inversions in this final array. Okay. So basically, this is the idea which we're going to follow. And let's see if so. Did you guys follow this, or should I explain it again once? I'll write a pseudocode for this. Okay. I don't see any specific doubts right now. Okay. So let's write the pseudocode for this. Pseudocode. So basically, we are first going to find the smallest element, and we're going to greedily pick which one to go with. Okay. So the idea is basically idea for I equals 1, 2, 3, right? Find the position. Find the position of this element in permutation. This element in permutation, and then um, number of larger elements to left. Okay. Number of elements to the left. Number of elements to left. Okay. If this is smaller, then stay as is. Then stay as it is. As it is. If this is smaller than number of elements to the right, number of elements to right, to right. Similarly, otherwise, convert to 2n minus p of I. Okay. And why are we doing this? We're basically saying that, see, if the current element is the smallest element which is active in the array, and the elements to the left will form inversions if it stays as it is. Meanwhile, the elements to the right will form inversions if we convert it. So whichever is smaller, we're going to pick that greedily. Okay, so it's basically a greedy idea. Greedy idea. Okay. Right. And one thing to keep in mind is, because we are processing its smallest element to largest element, once we have fixed the value for a smallest element, it will not change no matter what we change the values of the largest elements to, okay, by the nature of the problem. So this observation which I wrote in red over here is very important and it is key to the solution. Okay, so basically if we have fixed the smallest element or the smaller element, then the larger ones, no matter how we flip them, they're not going to change the count of inversions of the smaller one. Okay, and yeah, and then basically, then once we have done this, we can say that um, current I is processed, current I is processed. So just remove it from the array for simplification, right? Remove it from the array. Okay. So let me just write pseudocode for this. So pseudocode for this will look something like this. For I goes from 1 to n, then so initially the vector will be simply the permutation. So vector v equals the permutation from input. Okay. Then what we're going to do over here is we're going to um, find position of I in v of I in v. Our answer will increase by the minimum of the two choices we have. The answer will increase by the minimum of two choices we have. Either we take the left, either we did the left thing or we did the right thing, in which case we flip the value of the array, right? Flip the value at this element. Like we did 2n minus p of I. So it will be basically comparing the amount of elements on the left to the amount of elements on the right. Okay, so it will be simply I, comma, the vector size minus I minus 1. Okay, so minus the current element position. Everything to the right is this one, and everything to the left is this one. Basically, we're taking the minimum of the two cases for the inversion. Fine. Now we can remove this element from the array. So remove element with value I from the array. With value I from array. Okay. And actually, so there's let me just rewrite this. So let this position be pos. Then I think I wrote I twice. So let me just clarify this. So it will be the minimum of pos, comma, v dot size minus position minus 1. So pos is the position of this element I in the vector. Okay. Okay. And then we can finally print the answer. Okay. Let's have a quick look at the code for this. So, okay. So the code is pretty short. We take in the input n. We take in the input of the vector, right? Initially the answer is 0. Then um, what we do is basically for each I from 1 to n, we're going to find the position of that element in the array. Okay, so we're going to do basically set the position equals 0. While a of position is not equal to the target, we can increase the position. Okay, so this is just a linear we go of n, we go of n to find position of I. Okay, and we can do this because the problem constraints goes up to 5,000, right? N goes up to 5,000. I should have mentioned this, but n goes up to 5,000. So n squared solutions are perfectly fine. Okay, n squared solutions are perfectly fine. So basically, we find the current position of this element I. We can add the minimum of that position versus a dot size minus post minus I. So basically, this is the number of elements to the left and the number of elements to the right. Okay, so inversion from this element equals min of left right. And why left right? Because if we leave it the same, the number of inversions will be the ones from the left. If we convert it to 2n minus p of I, the number of inversions will be the inversions from the right side. Okay. Then we erase this from the array because now it does not matter for the future values. It will just affect the answer, right? So we erase this from the array and we continue with this loop. Finally, we can print the answer, which is the total sum of inversions. Okay. So this is the code for the problem D. Yeah. To be honest, D felt pretty hard for me. I would say it's at least 15, 1600, but I don't know. There were a decent amount of solves. I think it's 1600 plus, in my opinion. Okay. So basically, the most important observation is if we process our array from the smallest to largest, basically what we're doing is our permutation, we're considering 1 first, then we're considering 2, then we're considering 3, right? And in that way, because we considered 1 first and all of its effects, it will not affect like 2. For 2, we do not need to consider 1 again because we have already considered 1 and we have greedily chosen the best path for that, right? So that's why this greedy strategy works, because once we have already processed 1, we don't need to, when we are 2, we can just delete 1 from the array and we can continue processing it. Okay, so that's how it works. All right, so that was problem D. For problem E1, I don't have my code. I saw this code from someone else. Um, I'll go ahead and explain it a little bit, or I'll explain the general idea, and obviously I'll share the code as well. But I did not solve E1 during the contest as well, although I tried E1. D I had no idea, so I didn't do anything. But E1 I tried. I had a small bug in my code, but yeah. Okay. So just give me a minute. I'll just have some water and then we can start problem E1. Okay. So E1 is an interactive problem. So if this is your first time with interactive problems, you'll need to go check out, some things to keep in mind while doing interactive problems, that we have to flush the output at each step and things like that. Okay. So I guess if you're reach even in the following even, you would know all that at least. Okay. So there is a hidden bracket sequence S, which contains only forward bracket and close bracket. Okay, so it's a hidden bracket sequence. Basically, our goal is to guess this bracket sequence. Okay, we have to guess the bracket sequence. It's like a normal interactive problem where we have to guess some hidden sequence. And we have to use it, you have to do it using not more than 550 queries. Okay, now what is the query type? Each query has the following form. We have to pick some integer k and pick k indices. Okay, we have to pick k indices. We can print these k indices, and note that the indices can be equal. Okay, note that the indices can be equal. Next, you receive an integer uh, calculated by the jury. And what is this integer? The integer is for the bracket sequence formed by these indices, right? For the bracket sequence formed by the values at these indices, T is the number of regular bracket substrings. Okay, the f of t is the number of regular bracket substrings in T. Okay, yeah, you don't need to flush. You can use endl, but then endl is also using flush again, right? So, um, yeah, that's what I meant. You need to know to use endl, and you need to know how to do fast IO in interactive problems. In C++, you can just do endl instead of slash n, and that does the job. Okay, so yeah. So basically, what we need to do over here is we need to find um, we need to find out the hidden string s, which is the hidden bracket sequence, and the only operation we are given is we can print some indices. And it's going to give us the number of non-empty regular bracket substrings. Okay, the number of non-empty regular bracket substrings in T. Okay, so in the given like indices we chose, it forms a string. It will tell you how many regular bracket substrings are there, and you can use 550 queries to find the answer. Okay, and then the format of the queries you can read. We need to put question mark followed by k, which is the number of indices, followed by the indices themselves. Then we will receive this integer, which is the number of regular bracket substrings. Then we can ask 550 queries. Finally, we need to print exclamation, and then we need to print s1 to s1, which is the hidden string. Okay, so this is the problem, and observe that indices can be equal. So we can repeat indices which we use here. Okay, in the string. Fine. So problem even. Okay. So now for problem even, um, so assume that so one more thing you need to observe carefully is it's given that guaranteed that S contains at least one opening bracket and one closing bracket. Okay, otherwise it will be very hard to solve. It will be impossible to solve. it is guaranteed that S contains at least one opening bracket and at least one closing bracket. Okay, so keep that in mind. And also the length of S goes up to 1000. So the type complexity does not matter very much for this problem. There's only 20 test cases. The length of n goes up to 1000. Okay, so that's also one more thing to keep in mind. Fine. So you need to know some properties of regular bracket sequences to solve this problem. And basically, if we have, okay, if we have, so the first property which I'm going to write, which will be useful over here, first property, if we have a character which is opening bracket followed by a closing bracket somewhere in the array, somewhere in the string. Okay, as long as, like, if we have some XX and then we have this opening bracket and then some more question mark elements, and then we have a closing bracket, there will be at least one regular bracket. There will be at least one regular bracket substring of this. Okay, there'll be at least one regular bracket substring of this. And why is that? Because let's say this was a closing bracket, then this would be a regular bracket substring. Otherwise, if this is opening, this is closing, then this would be, otherwise this is opening, 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 and then this would be a regular bracket substring. Okay, so we can show by induction that if there is one opening and one closing, and they're after each other, the opening comes before the closing, then f of this will be at least one. Okay, the f of this will be at least one because there's one opening, one closing here, and no matter where, what values we choose over here, there will be one regular bracket subsequence. Okay, at substring at least. Fine. Okay, so this is the first property we need. Okay, which you need to keep in mind. All right. Now the second idea which we're going to use over here. So this is a interactive problem, right? So you basically somehow any way you want, you have to figure out the answer from the judge. You need to figure out this hidden string. So that's why it will seem like these properties are unrelated, but basically what we're trying to do is somehow figure out the answer. Fine. Now the other thing we want to do is we want to find at least one opening bracket position. Okay, at least one opening bracket and one closing bracket. Okay, why we try to do this? Because using the queries, we want to find at least one opening bracket and at least one closing bracket. And the reason we are trying to do this is because, um, well, it'll be apparent later, but once we have that, we can use some techniques or use some specific strings to find out the values at other indices. But for that, we will need at least one opening bracket and at least one closing bracket. So I guess trust me on this. I'll show you why this will be helpful later. Okay. So how do we approach this sub problem? We basically have an unknown string, completely unknown string, and we have this only this query which will find for the given indices when you take substring, is it regular bracket sequence or not, right? So we just have that type of query. How do we find out? Okay. So first thing we'll do is what about a query for all the values? Okay. What if we have a query f of 0, 1, 2, 3 till n minus 1? Okay. So for all the positions, if we take f of that, okay. So f is the count of regular bracket substrings. So what if f of whole array, okay, or whole string is equal to 0? Okay, if f of the whole string is equal to 0, then you can see that the string must be something like this: closing brackets followed by opening brackets. Okay, if f of the whole string is 0, then it must be some bunch of closing brackets followed by opening brackets. Okay, basically what I'm saying is if you ask a query, we're going to do a query which will be like k will be simply equal to n, right? N elements, and the elements are simply 1, 2, 3, 4, 5, 6, 7, 8 till n. Okay, and if this is 0, if answer for this query for query is 0, then we can say that the string must be something like this. We know that there's at least one opening bracket and one closing bracket, so it must be some closing brackets followed by some number of opening brackets. Okay, so now we can simply find the opening bracket will be the last element, right? In this case, the opening bracket will be the last element. So this last element will be the opening bracket. right? And then this first element will be the closing bracket, right? So we have found a pair of opening and closing brackets. Okay. So I hope that's understood. Okay. Now what if this query gives a non-zero value? Okay. F of this query is non-zero. F of query, F of query is not zero. Okay. So for this, we're going to use binary search. Basically, we're going to use binary search and figure out one position of opening bracket and one position of closing bracket. And how will we do that? Basically, let's say this is our string. So this is our hidden string, which we do not know about, right? But let's say this is our hidden string. Okay. Now f of this is non-zero. F of the whole string, if we just put all the values of the string from 1 to n, that is not zero, and we know that. Okay. Now let's say f of half the string is also not zero. Okay. F of half the string, if we start at middle position, let's say middle position, go to the last position, this substring, so mid plus 1, and so on, is not zero. Okay. So that will mean that there's some opening over here as well as a closing over here. Okay. So that will mean that in this side, there's the opening bracket as well as the closing bracket. So basically, we're halving our search space each time to find the opening and closing bracket. And then finally, let's say um, at this position, you can see that f of this substring, so f of this position, let's say this position is x, then f of position x, x plus 1, if we query these positions, we can see that this f of x is equal to 0 over here. Okay, this f of x becomes equal to 0. And when f of x becomes equal to 0, okay, so here, this is the point where f of x became equal to 0, right? Here f of x became equal to 0. Here f of x was not equal to 0. Okay, if f of x was not equal to 0, then we can find out that this must be a closing bracket, right? We can show that this must be a closing bracket, and also this must be a opening bracket. Okay, opening bracket. So again, we have found position of at least one opening bracket and position of one closing bracket. Okay. So basically what we're going to do is we're going to binary search until we find the position where f of x equals 0. Then we can say that this position is the closing bracket and this position is the opening bracket. Okay. So I hope you understood how we are finding one opening bracket and one closing bracket in the given question. Okay. So if simply the f of the whole array is 0, we can simply take the first and last. Otherwise, we can show that if this is f of x 0, this is f of x not 0, then this must be opening and this must be closing. And why can we binary search? Because we can binary search because this will be monotonic, right? Here f of x will not be 0. For this whole area, f of x is not equal to 0. And for this whole area, f of x equals 0, right? For this whole section of the string, f of x will be 0. So that's why this is monotonic, and we can binary search and find this position. We can find the opening brackets and the closing bracket. Okay. So we can have a quick look at the code. So this is not my code, someone else's code. So basically, what they've done is they have made a ask like helper function which takes in a vector and prints the size of that vector. It prints all the elements indices in that vector and it returns the answer. So this is just a helper function. Then what they're doing over here is iota is a function which fills the numbers 1, 2, 3, 4 till n in the array. Okay. So if this value was positive, right? So if f of this whole string was positive, in that case, we need to find the exact position. We need to binary search and we need to find the opening bracket and closing bracket position. So what they're doing is they're doing a binary search and they're finding the exact point where f of x becomes 0. Once f of x becomes 0, this will be the value at r. The position r of the binary search will be here. The position r minus 1 will of the binary search will be here, right? So they put opening bracket as r minus 1 and closing bracket as position r. Okay, so you can have a look at this code. I'll post this after the PCD is done, right? Or you can pause it and you can see. Basically, this code finds the position of the one opening bracket and one closing bracket. Okay, so it is guaranteed to find at least one opening bracket and one closing bracket, right? All right. And otherwise, if f of the whole array was itself 0, we can show that closing bracket will be the first element and opening bracket will be the last element. Since there is at least one opening bracket and at least one closing bracket. So I hope this is clear. Okay, Dom was stuck on D. That is nice to know because I also got stuck on it. How will you determine how many closing bracket and opening bracket are there? We are not determining how many opening and closing bracket are there, Pradeep. We just want to find any one closing bracket and any one opening bracket. That's what we're trying to do so far. And the way we have done that is basically show that if we find, so like basically what I'm saying is f is our function which basically says how many proper substrings are there, right? How many proper bracketed substrings are there for a given string. Okay. So what we are doing is basically when we choose a value mid in our binary search, when we choose the value mid of our binary search, let's say this was the position mid. What we are going to do is we're going to query the positions. We're going to query the positions mid, mid plus one, mid plus two, so on until n. Okay. So basically we are querying some substring of the string and we are checking if that value is 0 or not 0. Okay. As soon as that value becomes 0, we can show that this happens at a closing bracket and an opening bracket. Okay. So if the whole array had a non-zero value and at some point it became 0, that means the remaining will simply be some closing brackets followed by opening brackets, right? It cannot be opening followed by closing because that was the first thing we showed. It cannot be opening followed by the closing if we want it to be 0, right? So this is to show that if there's an opening followed by closing, it will always be greater than or equal to 1. So because it has become 0, this element has to be a closing bracket. This element has to be an opening bracket. I hope you got that. So basically with this method, we found position of one opening bracket and we found position of one closing bracket. Okay. All right. So now after this, how do we continue? We have the position of one opening bracket and we have the position of one closing bracket. There are many different queries which can help us, but one query which has been used in this code, and I'll show you that. So basically the intuition is over here. Since binary search, let's say binary search, which we did, let's say that took, let's say 20 queries, right? Maybe 20 to 30 queries would have taken. N is at most 1,000, so it's not much. At most 20 queries would have been taken. Now let's say we have like 500 queries left, 500 queries left, and the size of the string is 1,000, right? Size of the string is 1,000. And basically the intuition is we want some kind of a way such that we can find at using one query we can find the value of two different positions. Okay, we can find the value of s of I1 as well as s of I2, where these are two different values. So basically we can find two values of the string at a given time. We can find whether they're opening or closing. Okay, we can find whether they're opening or closing of two different values using one query. Using one query. Okay, so that's what we're going to do. And there are many different structures which are possible. The one used in this code is basically this. So question mark, closing bracket, question mark, closing bracket, opening, closing bracket. Okay. So since we already know the position of an opening bracket and the position of a closing bracket, if we want to query the substring using this opening and closing, we can just put the position of opening bracket here, position of closing bracket here. Okay. So what are we querying over here? Our query function will be something like this. Basically, it will be cout. So we want to find two indices I1 and I2. Okay, we want to find the values at the two indices I1 and I2, and that's what we will solve. So we'll cout. So these are six total characters. So six characters. First will be the position I1, right? Then will be the position for opening bracket. Sorry, closing bracket. Closing bracket. Then will be the position I2. Then will be the position closing bracket again. Then it will be the position of opening bracket, and then it will be the position of closing bracket. Okay. So we will output this and we're going to figure out the answer using this. And yeah, then we'll see in X and we'll decide the value of S of I1 and S of I2. Okay, we'll decide the value of S of I1 and S of I2 using the output what we got from this query. Okay, so basically what the query is forming is it is forming this following string. The string which is formed is basically S of I1 with a closing bracket after that, right? With a closing bracket, um, then S of I2 followed by closing bracket, followed by opening and closing. Okay. And based on the answer to this query, we can find exactly the value of I1 and I2. Okay. And let me show you how that is. So let's make a table. Okay. What are the possible values of S of I1? What are the possible values of S of I2? Okay. So we get query, right? Our query is basically like question mark, bracket, open, close. Okay. Query, value received, value received. Okay. Now it is possible that both of these are opening brackets. Both of these are opening brackets. Or it's possible that this is opening, this is closing. Or it's possible that this is closing, this is opening. Or both are closing brackets. These are the only four cases possible. What will be our query in these four cases? Opening, closing, opening, closing, opening, closing in this case. Here it's opening, closing, 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 opening, closing. Here it will be closing, opening, opening, closing, opening, closing. Here it will be closing, closing, sorry, we yeah, there should be two closings, right? Two closing, closing, and then closing, closing, and opening, closing. So this is basically what will be what do you say? The judge will receive for the four cases of S of I1, S of I2 values, right? So for this value, the judge is basically going to try and find the count of um, valid bracket sequences in this, and valid bracket sequences in this, valid bracket sequences in this, valid bracket sequences in this, and that's the response that the interactor is going to give us. Okay, the interactor or the judge will give us the number of valid bracket sequences in this, and if these four are unique, we can show that we can decide exactly the value of S of I1 and exactly the value of S of I2. Okay, so in the first case, how many valid bracket sequences are there? 1, 2, 3, 4, 5, and 6. So the value we will receive is 6 over here. Okay, as you can see, the value we will receive is 6. Now, what about the second case? The number of valid sequences will be 1 and 2, right? And these are the only valid sequences which are there. Value received will be 2. Okay. In this third case, the value received will be 3 because there are 3 total valid sequences here. And in the last case, the value received will be 1. Okay, so as you can see, for the different values of S of I1 and S of I2, we can determine exactly which one gave us which value. Okay, so if we give a query like this, 6 I1 plus 1 closing bracket plus 1 I2 plus 1 closing bracket plus 1 opening plus 1 closing plus 1 and L, right? That's why we found the position of opening bracket and closing bracket, so that at least one opening bracket position and one closing bracket position is known to make this kind of a query. Fine. So now that we have found this and we can put these queries based on the four different values, we can decide what was there at I1 and I2. Okay. So using one query, we're able to decide for two positions. Here, using one query, we can decide I1 and I2 for two different positions. Positions values are found. So easily with 500 queries, we can find all the 1,000 positions of the hidden string. All the 1,000 positions of the hidden string. Fine. So that's the idea here. Let's have a quick look at how this is implemented. So basically, once you have find the closing and opening positions, either binary search or using the way we discussed earlier, um, we are going to ask basically I plus 1 closing, I plus 2 closing, opening, closing, right? So for each element I and I plus 1, we're going to push them into, we're going to find their values over here, and um, if the response is 6, we know both are opening. If the response is 2, we know one is opening and one is closing. The first one is opening, the second one is closing. If it's 3, we know it's closing followed by opening. Otherwise, it's both closing, right? So that's how we saw that the responses would be. And then finally, if the last element we might need to ask separately, the last element we might need to ask separately because if it's odd numbered, and then we can simply see out that. Okay. Okay. How do you think of this in contest? The reason is because it's pretty simple, right? The main idea, which the first thing which you should think of, we have less number of queries and more number of elements to find. So what kind of query will give me more information, will give me information for more than one element using only one query. Okay. And I guess the harder versions of the problem are simply using one query, find the information for 5 different elements. So that's the medium one. Using one query, find the information for, I think, 10 different elements. That's the hard version, right? So if you can figure out the solution to those, you will be able to solve the harder versions of the problem as well. So this is one construction which will find which has different values based on I1 and I2, and it gives you using one query the information of two different indices, right? And once we have formed this construction, you realize that, oh, I need one opening bracket and I need a position of a closing bracket. So then you can think of the binary search to find the opening and closing bracket. So in a contest, you would think of this part first, and then you would think of this part later. But to explain, I explained them like that. Okay, yeah, I guess this contest was a bit harder. Can I do PCD for ad coder as well? I'll put forward that suggestion, but yeah. Right, as of right now, we do not do ad coder PCDs, but yeah, I can put forward that suggestion. It was so hard. Yes, it was a bit hard today. Like I got stuck on D, and on even I had some implementation problem. I had pretty much almost the similar idea for even, but I had an implementation problem. I'm not exactly sure why my implementation is failing. I guess I'll check it out after the contest. This is someone else's implementation, but yeah. All right. Any general doubts now? We can pick up general doubts or any doubts related to the previous questions. Today was on the slightly harder side. I think D was at least slightly harder than usual, I would say. So it's fine. What's my lead code ID? My lead code ID is accordance. Um, I think this is my lead code ID. Although I very recently started lead code, mostly for the PCDs. Yeah. As you can see, it was a very old account, but I only started doing contests now. Yeah. C was harder. I didn't feel C much hard, but I can understand why it was harder because it asks some graph type of thingies. I didn't find C that hard, but yeah, I can see why it would be considered hard. And yep, looks like I am also losing rating. I think for a specialist, solving 3 questions in good amount of time is enough to maintain the specialist rating. So that's fine, right? As you can see, expected performance. Okay. How much time to master graphs? That depends on you, to be honest. But maybe a month or two of practice will be enough. Yeah, a month is more than enough to master graphs. You have 30 days to OA. You can master graphs in 30 days for sure. Especially for like OA level, I guess. What are the topics for question D? Okay. It's mostly constructive in my opinion. Like this is very constructive style question plus greedy. Like to be honest, today's questions were very much about intuition. So it's very hard to give topics, but problem D will be mostly like, yeah, it would be constructive and greedy, in my opinion, for problem D. Do I practice topic wise? I used to practice topic wise. Sometimes I even do now when I see some new topic, I practice it for a few times. But yeah, during my training, when I got a lot of rating, at that time I was definitely doing some topic wise questions. Yes. You watched DSU lecture but couldn't solve which one? The problem D, problem C. Which one I talk about? Problem C. Problem C was not really DSU. So I don't know why you're talking about DSU here, but yeah, problem C was not DSU. Which question I talk about, Raghav? because I didn't use DSU for any of the questions. C. C is less about practice, it's more about understanding how graphs work exactly. So definitely go through the solution again. It did not use DSU. It just used the idea of union of segments. Yeah, yeah. You can go through the video solution again. It was not even using graph, any algorithm. It was mostly the idea of how graphs and intervals work. You just had to make two observations. Like I said, the first observation was if you keep the starting points always different, there will never be a cycle. So once you have that observation, you can solve it pretty easily. I'm level 100 and I solved two questions in 3 hours. Will I get minus? I am not sure. It depends on how much time and penalty also you took, right? So I can't tell you right now. But yeah, two questions is fine for 1100, I think. C was a bit on the harder side. Okay, then, guys, it's getting a bit late, so we'll end the session now. Do check out Eliminators course again if you haven't. I guess the sale is over now, but still, do go ahead and check it out if you want an ordered and structured approach for your CP learning. Oh, looks like the sale has been extended for another half a day. So yeah, go check it out. All right then. Thank you for attending the session. Yeah, it is 120. The contest was 3 hours this time, right? Um, Hope you learned something and see you next time. Yeah, bye bye.